Welcome to Module 4. Now we start to really get into the heart of what statistics is. If all we could do with statistics is collect data, make plots, compute numbers, statistics wouldn't be particularly useful, and you probably wouldn't be taking this class. So let's look at what we really want to use statistics for. What we want to do in statistics is we want to make a generalization about a population from data we collect from a part of that population, our sample. And to be a little more specific, we are interested in a particular variable in that population, and we want to know the value for that variable's parameter. And what we're going to do is we're going to go ahead and estimate it from our sample. And so this process of taking our sample statistic and using it to say something about the population parameter for that value, that's called inference. And probability is how that process works, or the basis for that process. And so this is important to understand. Probability is the reason why statistics is valid and it works. It's important to understand that statistics has a lot of problems with it. Right? In the last module, we saw that people can misrepresent, results using statistics. And we know for a fact that statistics can be wrong sometimes. So why use statistics? Why not use another method for making decisions? Say like astrology. Astrology seems to use the same sort of process on the surface, right? We ask a question to the astrologer. They collect data. Maybe they read our palm or they ask our birth date. They summarize the data. They go to charts and they have various books and they do calculations and all this sort of stuff, and they make a decision. So what is it that makes statistics different or more valid than astrology? And it's the fact that there's a rational basis for statistics. And this is probability theory. We know for a fact probability theory is true because it comes from mathematics, and we prove things in mathematics. So this is how probability theory, and we're going to talk about the process of how this works. This is where probability theory comes into inference, so to speak. It's going to answer this key question that we touched on very briefly in the first module, which is how likely. And so it's going to be the basis for this rule that we just kind of like pulled out of nowhere when we were talking about statistical significance, right? We said if something's less than 5% likely to occur, it's statistically significant. We're going to talk about what that means and where that 5% comes from. But that ends up coming from probability theory. And so in this particular module, I'm only going to look at just the probability theory we need to do inference, okay? So first of all, I'm going to kind of motivate the type of probability theory that we're going to be looking at. And it's going to be related to measures of relative standing. And that's what we're going to focus on. So we're going to talk about the first measure of relative standing, which is called a percentile. We're going to answer the question, well, what is a percentile? And then we're going to learn how to compute percentiles using both sample data and probability distributions. Again, we come back to this theme over and over again relating to what one of my statistics professors said, which is that the most dangerous word in statistics is what? We always have to be aware that the sample and the population have the same things. Okay, they both have averages, they both have distributions. And so you always have to specify what are you looking at? Things from the sample or things from the population? And this particular topic is going to be devoted to just one video. And then we're going to go a little bit deeper, and we're going to talk about a second measure of relative standing called the z-score. We're going to answer the question, what is a z-score? And then we're going to learn how to compute it using sample data and population distributions. And so I'm going to kind of jump around in the text a little bit because, again, I only want to pick out those portions of the book that we just need to do inference for right now. So we're going to cover sections 3.3, 6.1, and 6.2 in the text. Although if you follow the handouts that I'm going to give a PowerPoint for each of these three topics here, and then do a video with it. If you can follow that, you should be fine. But if you want to go back and get more information or maybe a little more in-depth explanation, the book will be there for you. But again, I'm just going to choose what we need for our particular purposes so we don't get overloaded and we can stay kind of focused. So first I want to talk about measures of relative standing with sample data. And if we kind of take a look at this, I'm going to introduce the basic problem that we're interested in by looking at a famous example. So in the 2008 Summer Olympics and the women's heptathlon, there were two contestants that really stood out. The one was a European long jumper. Her name was Natalia Dobrinska, and she had an incredible long jump. She beat everyone else in the competition by more than half a meter, and she set a world record. But there was also a really good sprinter from the US, Hialeah Fountain, and she actually set a world record in the 220-meter dash and beat all of the other contestants by 1.5 seconds. Now, the question is, who gets the gold medal? These contestants were actually relatively similar in the rest of the events. And so we have this problem of how do we compare the performance of two people when they come from totally different areas, right? So in the case of Natalia, she had a distance that we're measuring. In the case of Hialeah, there's a time. Longer distances are better, shorter times are better. So how do we even compare these two people? And it turns out this sort of problem actually occurs a lot in business and everyday life. And so we're going to look at a few examples here. This is one that you might deal with when you're actually out in business. Okay, you might have to lay off a person in a division that you manage. And we're going to have to decide between two people, Barb in accounting and Bob in IT. But notice that we can't compare them directly because their job duties are different. They do different things. So how do you determine which is worse? This is kind of like the flip side of the Olympics problem, right? Here you want to look at who is underperforming rather than overperforming most. Another example that you're probably going to have to deal with when you graduate, you're going to be getting a lot of job offers. And let's suppose you get two job offers at places you really like. And the first is in Washington, D.C., and they want to give you $60K. And the other is at Daytona Beach, and they want to give you $50K. Now you might say, well, Matt, it's not apples to oranges because we're looking at the same thing. We're looking at, money. But we have to remember that $60,000 in Washington, D.C. is not the same as $60,000 in Daytona Beach because there's a difference in standard of living. So again, it's an apples to oranges sort of comparison. And the last we're going to look at is just for fun, okay? And people like to do this. They like to compare athletes from different eras, okay? And we're going to look at a famous historical example where we compare two Major League Baseball home run hitters, Babe Ruth and Barry Bonds, and we ask the question, which one is different? And the reason why this is an apples to oranges is Babe Ruth played back in the 1920s, and Barry Bonds played around the 1990s and in the early 2000s. So they come from totally different eras. And so that's going to be a fun sort of problem to look at. And this is one way in which measures of relative standing are going to come into play. But we're going to look at also populations, not just sample data. And this is an important part of the intro because this kind of ties into what we've done in the last module and what we're going to do in future modules. And there's going to be a hypothetical problem that we consider here. So we're going to be interested in a study that was performed at the University of Chicago back in 2011. And they wanted to answer the question, are rats empathetic? And what they did was they had one rat in a closed container, so you can see the rat in the closed container, and there was a free rat, and they wanted to see if the free rat would let the caged rat go. And they had various incentives, right? They would offer the free rat chocolate and ask the question, do they prefer to eat chocolate or would they prefer to help their buddy? And what they found out was that 19 of the 24 rats in this study opened the door. Now, what can we conclude from that? So this goes back to this question of statistically significant. What would we expect if the rats were not empathetic? Well, we might think they're indifferent, right? 50-50 chance, like flipping a coin. They either help or they won't. So let's suppose only 50% of the population would open the door. What would we expect to see? Well, we'd expect to see 12 of the 24 rats open the door. It's like a coin flip. If you flip the coin 24 times, right? 50% chance each time you're going to get a heads. We'd expect to see 12 out of 24 of those flips come up heads on average. But we also know there's variation, right? If you flip a coin 24 times, it's probably not going to come up exactly 12 heads. There's variation. So we wouldn't necessarily expect exactly 12. It might be a little higher. And we know our sample size is small. And we discussed back in the first module how the reason why we like large samples is our estimates are going to be precise. They're going to be really close to the actual value. So maybe we could have got 19 just because we have a small sample. There's going to be variation from sample to sample, and with small samples, there's actually a lot of variation, right? If you flip a coin 3 times, you're going to find out that it actually occurs that you get 1 heads out of the 3 tosses a decent amount of time, even though, it should be 50-50, right? But we still get a pretty far departure, 33% versus 50%. So how do we answer this question? This is a hard question to answer, and we're going to actually spend this module and the next 2 modules starting to discuss this. So let's go back and try to understand what we did in the last module and why. So in the last module, we spent a lot of time talking about histograms and adjusting the bin width. And what we were trying to find, we were trying to adjust it so that it would fit a nice smooth curve. So we said, okay, 4 bins is too few. It appeared kind of chunky. 8 bins is too many. It appears too choppy. There's too much variation. And we get 5 bins, we can see we can kind of fit that to a nice smooth curve. So we wanted to choose as many bins as we could and still be able to get this nice smooth fit. And the question is why? Why did we do that, right? So here's the reason why. This population curve, this curve that you're seeing in orange, is an estimate of what we think the population would look like. In other words, if you took more and more and more larger samples, more and more data, we would think that it would begin to approach this nice smooth curve. And this population curve is important because this is where we're going to go to make our decisions in statistics. And notice this question, how likely could we get our result by random chance? How likely is it that if the rats were indifferent, we could get 19 out of 24? And it turns out this question, how likely, is actually code word for percentile. And that's going to be our first measure of relative standing that we're going to study. And how is this related to this population curve? We're going to see that percentiles are areas in the tail of the population curve. Let me flesh out this point a little bit. What we're going to see is that very often we're going to get curves that kind of look like this. They're symmetric and unimodal. And we're going to want to know how likely is it that we could get some particular value from our sample. I'm just going to call it X. And that word, how likely is it we could get X, is equivalent to asking what is the percentile for X. And that percentile, we're going to find out, is the area in that tail of that population's curve. So I'm going to take the tail of the population curve where X is, and that area is going to be the percentile, and that's going to tell us how likely. Now, when I work with a lot of you, when we do these Zoom sessions for office hours, it's not uncommon for people to say, oh, I see, now I get the logic. And you're exactly right. This is data logic. This is how we make decisions using data. This is the reasoning. And it's not something that anybody would figure out on their own, myself included. Okay, I can definitely tell you that. You have to be shown. But once you're shown the logic, then you understand it. And if this doesn't make total sense right now, that's fine. We're going to come back. We're going to keep fleshing out this logic and showing in more and more detail how it works using concrete examples so you understand it better and better. Now, where does probability theory come in? Maybe I'm just telling you this and this is a figment of my crazed imagination. Okay. Here's how it comes in. So we use probability theory, and it's just really a branch of mathematics. It's not even part of statistics, okay? It's a collection of things that we know for a fact are true because they're proven mathematically. What does this have to do with statistics? Well, the key thing about statistics is we have variation. If everybody was the same height, there was no variation, say, in some variable like height. Or there was no variation in the likelihood you could get a certain value. In other words, it was equally likely that every single height was possible. We had a uniform distribution. There would be no probability. So probability comes in because we have variations in the value that a variable can take on, and we also have variations in how likely it is it can take on those values. And you might say, well, that sucks because everything varies. How can we tell everything? How can we ever tell anything, right? It just seems kind of random and chaotic, but it's not. The key point is that this variation in the data, it forms patterns. And one of the patterns we're going to talk about is this bell-shaped curve known in statistics as a normal distribution. We talked about how standardized test scores have this bell-shaped curve. We also talked about how physiological measurements have this bell-shaped curve too. And by the way, this is actually real data in both of these cases. And you can see the sample data forms a histogram, and then we can see it's fit to this population smooth curve. And this smooth curve from the population, that's the bell-shaped curve. Okay, so that's nice. Well, what does that tell us? Well, where probability theory comes in is probability theory actually lets us quantitatively describe this pattern. I mean, it's an amazing fact. I don't know about you, but I find it amazing that all these different types of data, standardized test scores, physiological measurements, we're going to see later on variations from manufacturers' claims. Like you go home and you take a box of Raisin Bran that says there's 16 ounces. If you measure it, it's not going to be 16 ounces. There's going to be variation about the mean. All of these different types of data form bell-shaped curves. And that just blows my mind. That in and of itself would be cool. But the way that we can use that to make decisions is the fact that all of these patterns, all of these bell-shaped curves from all these different data types are all given by the same type of function. That's an amazing fact. Now, you're not going to have to memorize this function. In fact, you're not going to have to even compute values with it by plugging into the function. Turns out StatCrunch is going to use this function, but it's already embedded. It's already programmed into StatCrunch. But this is the reason why StatCrunch gives you answers that allow us to make decisions, because this pattern can be described mathematically. And so we're going to see that we can compute the areas in these tails. We can compute the percentiles that we're interested in to answer this question, how likely something is to occur, and then we can make a decision based off that. And we're going to fill in these blanks, but this is the basic logic and where we're going in the next module. So thanks for listening, and stay tuned.